All right, guys. Here we are on second section of the first chapter, and hopefully you did okay with the work from last video, and are getting a little bit used to the concept here of what we're doing. So we're going to move on, and we have more definitions to go through and
Yep.
more terminology here and
Major
vocabulary.
idea though in geometry with the congruence coming up here.
Oh,
That's a
absolutely.
big
Oh, yeah.
deal.
Use it all year.
Yep.
Yeah. So we do have a definition here called postulate that has to do with maybe like a phrase that we'll have or a rule, as this says, and it's just accepted to be true. We don't have to go through and do a full proof on it. We don't have to give reasoning for it. We just accept it to be that way. It's one of the concrete foundational pieces of geometry, and so we just use it. We just assume that it's true based on that. Sometimes it's also called an axiom. And so a postulate or an axiom, and we don't get real picky about the distinguishment between a postulate and what we'll have later called a theorem, and but it'd just be good if you knew this term. We don't use it a ton, but just so that you know that it's there.
The way I like to think about postulate is the idea of gravity, guys. You've never proved gravity, but everybody understands it. You know that if you drop your pencil, it's going to fall to the ground. You guys get that idea, so you've never had to sit down and prove that it's there.
Mm-hmm.
And that's kind of the way I think of a postulate. Is we just get it.
Yeah.
We just know it's true.
Yeah, it's good. So here's our first one, and it's called the ruler postulate. And again, we don't go through and prove this. We just look at examples of how it works. But the ruler postulate states that the distance between A and B, so 2 points on a line, the distance between A and B, notice how that notation is. Mr. Bedell referred to this in the last video. Sometimes we have the two letters with nothing over the top. And that's what that means, is the distance between those 2 points. So when there's nothing there, it doesn't mean segment or line AB or ray AB. It just means the distance between those 2 points, or in other words, the length of that segment. Okay, is the absolute value, so there's a term from Algebra 1,
Yep.
absolute value of the difference between the coordinates of A and B. And remember, the coordinates are just the numbers that correspond to point A and point B. And so really, the ruler postulate just means the distance between 2 points.
Yep.
That's what it means.
And it's kind of this idea in geometry that there's no such thing as a negative distance.
Right.
What I mean? We always think of anything we talk about in geometry, guys, is when we talk about a distance, it's always or measurable outcome. It's always going to be positive.
Yeah.
I mean, when you drive from your house to school, let's say it's 10 miles. When you go back from school to your house, you don't call it, well, I got to travel negative 10 miles back to my house. You say, no, it's still 10 miles back to my house.
Yeah,
That's kind of the idea.
It's a negative 2 feet.
Yeah, exactly.
Yeah. So.
Okay, so more on the ruler. That if you look at this, and that is, what is that, 2¼ inches? Yeah. That, I mean, it's just basically you can look, the ruler postulate says is that we can take a segment, put it up to a ruler here, and measure that and come up with a number.
And notice we're not starting at 0.
Yeah.
That's kind of the concept here, is we're not starting at 0. You don't have to put 0
right.
As the starting measurement place on a ruler. It's just saying that any 2 points, you can find the distance between them. Yep. Anywhere they land, on a number line or on a ruler or whatever you want to call it.
That's right.
And so I think they're just going to move it around here. That is the same thing as this.
Oh yeah, and those would be congruent.
They would be. They would be. It's just slid down.
Yep.
And it's just the same thing. So we're talking about using a ruler to measure.
Yep.
And so to measure this length, says to measure the length ST of segment ST to the nearest tenth of a centimeter. Well, we're not expecting you to put a ruler up here to your screen that you're watching this on or whatever. And I don't know, maybe you don't have a ruler that measures in centimeters, but most of them do anymore. Most of them have inches on one side, centimeters on the other. And so you just need to be familiar with what the scale is for centimeters. But this ends up being, when you put the ruler up to that, and here's a metric ruler, that it ends up being 5.4 centimeters because the ruler is marked in cm there. And so the big units, 1 unit, 2 unit, 3 units, are centimeters. And those notches in between, the marks in between, would be millimeters or tenths of a centimeter. And so as you line up that centimeter ruler to that, it comes out to be from 5.4, sorry, is where the T ends up being. But they're lining up the S with the 2. And so in order to calculate the length of that segment, you would subtract those two numbers to get that length. And so that's what they do inside of absolute value signs, because again, it has to be a positive distance. And so the length of that segment ends up being 3.4 centimeters.
The whole idea behind the absolute value here, again, guys, is that if you started at T and went back to S, even though, or you said, you know, you did 2 minus 5.4, you would get a negative 3.4, but we wouldn't want to say it's a distance of negative 3.4. We would just say it's 3.4. We don't include negatives when we talk about distance. I can't really stress that enough. It's always going to be a positive distance.
Yeah. Okay. So the length ends up being 3.4 centimeters for the length of that segment ST. Okay, using the ruler postulate.
Okay, so we have this. It's weird.
This is actually a hard definition.
Yeah, I mean, between is kind of a hard one. So
because you use it all the time,
we use it all
we're
the time.
using it very specifically.
Yeah. So any middle point of 3 collinear points is called between, and so you know, just look at the drawing that comes with it, and it'll make a little bit more sense here. But so if we look at, you know, the piece here, JKL, we could say that K is actually the between point, right? Mm-hmm. But based on that definition, it's kind of misleading because it says any middle point. And so what you guys might think of middle is the exact spot where it's the same distance from, halfway in between. Thank you. It doesn't have to be. Middle is anywhere in between those two points that they're talking about. So just be careful.
That's why this is a hard term to define, because technically in a definition you can't use the word in the definition that you're defining.
Yeah.
But it's hard to define between without saying, well, it's the point in between the other two.
Right.
And so, but that's all it means. It's just as long on a line, as long as there's a point, which we could come up with other points. Let's say that we came up with an N and a P and a so on between K and L, and I just used it. It would be between those because it's on the line between those other 2 points. And so it's always a comparison of being between 2 other points.
It's kind of like the rows in our classroom. You know, if you look at the row you're in the front, and then maybe your friend's in the very back, and then you have all those other students in between you in the row of your desk. Mm-hmm. It's kind of the same idea.
Yeah, but somebody in another row is not between.
That's right.
Because they're not in the same row. They're not in the same line.
That's right.
So, yeah.
Rows and columns.
Yeah.
So congruent, this is a huge word here, guys.
Yeah.
Congruent means when 2 objects have the same length. We use the symbol congruent, and it should pop up here, and there it is. So what's the actual? Is there a specific name that goes with this in Latin or something? Usually have those type names for those.
No, not that I know of. No. Yeah, but what's the difference between congruent and equal, though?
Yeah. So equal.
Why do we have to have this?
Once again, it's that, to me, I think of it as we have to have a way to differentiate between when we're talking about it visually and when we're talking about it mathematically. Mm-hmm. And so when you see the congruent symbol, we're talking about it visually. And when you just see an equal sign, we're talking about it mathematically. So it's this whole thing of geometry is always on 2 planes, the mathematical plane and the visual plane, and we kind of bounce between those all over the place. And you got to be able to look at something and just by the symbols tell, okay, do they want it mathematically or do they want it visually? And that little, what's that little squiggly on top called again, Kevin?
Tilde.
A tilde, sorry, I always forget that word, lets me know that, okay, they want visual. Right. And if there's no tilde, okay, they want mathematical.
Because in math, really, the only place we use congruent is when we're talking about geometry.
Yep.
And so when we're talking about physical, visual, concrete examples of shapes or lines or segments or whatever, that's when we use the congruent symbol. But guys, it's critical that you understand the congruent. We use it all year.
All year.
And we use it, we'll use it 20 times in a homework assignment or whatever.
Yep.
And so you just got to know what congruent means. It's just 2 objects have the same length. Okay? Or same measure. Probably that would be a better term here, is they have the same measure, because we can talk about 2 congruent angles,
right, or
and
shapes.
We don't measure the amount of an angle being a length, and so, okay, yeah, our shapes could be congruent, and so they're not a length either. So if we have a segment,
AB,
and another segment,
CD, and we could say that if we said that AB,
if they tell us.
Now look, this is really cool because this is the first time you guys get to see mathematical and visual kind of collide with one another. Notice that on AB, there's no segment symbol above it. It just says AB and then has an equal sign of 5. And so then it says CD also equals the measurement of 5. So there's the measurements, but then from that we can conclude that, okay, so if they actually measure the same distance, then visually they're the same distance as well. So we can go from the mathematical and transform over into the visual and kind of make some some deductions out of that.
Yeah.
And so basically, since the measurements are the same, then visually they're the same as well. And
Yeah,
so,
the other thing we'd like you to understand about congruent is if two things are congruent, that means you could basically slide one on top of the other one and they'd be exactly the same thing.
yep.
So when we're talking about segments, we could take AB, slide it right on top of CD, and it'd be the exact same segment. But we label it differently still. Or again, if we're talking about congruent angles later, you could take one angle, slide it over on the other one. It would look exactly the same.
Yep.
And so that physical representation that Mr. Bedell is talking about there, the visual, is what congruent has to do with. Okay? But understand they have to give us the fact that A, B, and CD are both 5 in order for us to come up with the conclusion then they are congruent to each other.
Yep.
Okay? So this is a segment addition postulate. And we use this over and over and over
This
again.
one's going to repeat a million times.
Yeah.
It won't be the word segment in front necessarily. You'll have
Right.
angle addition
Addition.
postulate.
Yeah.
You'll have the shape addition postulate where if you take two shapes and you add pieces to them, they're
Right. Area addition.
Yeah, that's the one.
Yeah. Yeah.
And so, I mean, it comes up over and over again, guys, and this is just the first installment of it.
And we're going to have another phrase that we use with this, and you'll get tired of us saying it, but it's got to get into your brain. So we're talking about adding two collinear segments. So we got to remember what collinear means. Collinear means same line. So two segments that lie on the same line in order to equal the whole segment. And so what we say is
part plus part equals whole.
We got to get
This
used to
plus
that.
this equals this. Yeah, it's
Yep.
real simple.
Yep. So if we have two segments, AB and BC, those two separate segments, we're going to add them up. Segment addition, we're going to add those two segments together to equal the whole segment. It's easier to see it as a picture here. So if we look at segment AB over here, segment BC, but notice they're those are two parts of the full segment AC. They make up part of a bigger segment because they're collinear with each other. And so when we add those pieces together, we can literally add the two lengths together and get the full length and get the full segment. So altogether that adds up to 18. The 5 and the 12 is 17. 0.8 plus 0.2 is another 1, so we add that 1 to it and get 18 for a total.
And here's kind of maybe another way for you to think about it, because you guys do have a lot of experience with this. Let's say from your house to school it's 18 miles, okay? And so let's say you leave your house, but on the way to school you stop by Marval's to get a breakfast burrito, and so Marval's is 5.8 miles of the distance it takes to get to school. Well, then you still have to travel the other 12.2 miles to get to school. And so it's that those two parts still add up to equal 18, even though you stop somewhere in between.
Right, right. Yeah, and B is between A and C here. And that's a critical part of that.
Yeah.
Yeah, yeah.
And one other thing,
ahead.
is notice that just because we're adding two segments together, those two individual pieces don't have to be the same length in order for this to work. It could be any two segment lengths that are collinear that exist between the whole overall distance. Okay.
Right. Right.
So don't think that those segments have to be congruent in order for this to work. It can be any two segments that are collinear, adding them together to go part plus part equals whole.
Yeah. Yeah. And of course these problems get a little bit more complicated. We'll throw in some algebra in here
Yep.
and so on to get pieces of those. And so,
Right.
But again, part plus part always equals whole.
Yep.
And so we're going to apply it to a map.
Yep. So we've got some cities shown on the map lie approximately in a straight line. Wish that would work out in the real world. Approximately in a straight line, use the given distances to find the distance from Lubbock, Texas to St. Louis, Missouri. So if you just look over there at the map before we even do this, just think about it for a minute. And remember the idea that part plus part equals whole. And so from Lubbock to Tulsa is 380, and from Tulsa to St. Louis is 360. Well, then all you got to do is go part plus part equals whole, and here's your equation. Maybe. One more. All right, just what I said. So we can just set up the idea that from L to S is LT plus TS, and so that is 380, which is the distance from Lubbock to Tulsa is 380, plus the different distance from Tulsa to St. Louis is 360, and we get 740, and so the whole distance is 740 miles.
So we're just adding up the parts to equal the whole.
Yep.
Yep. Another example, instead of on a map, but just on a number line. And so this is a little bit backwards.
Yep.
We're looking at part of it being FG. The other part is GH, but they don't give us that. Instead, they give us the whole. But we still know that the part that's 21 plus the other part that's missing adds up to the whole, and so we can calculate that. And so we can go through that process to get there using the segment addition postulate still. And so using the segment addition postulate, we would say that FH, the whole thing, equals the two parts added together, FG plus GH. and then substitute in what we already know. So FG or FH, the whole thing, is 36. Part of it is 21. We don't know the other part, so we could call it GH or we could call it X from algebra if that is more comfortable for you. And then we're just going to solve that equation in order to figure out what GH has to be. And so as we go through that and subtract 21 from both sides, GH has to be 15. Now some of you can just look at that diagram and say, well, if that whole thing is 36, part of it's 21, the other part has to be 15 in order to add those up. Or you can look at it as the whole thing is 36, part of it's 21, so you just subtract those and you get what's left over of 15. All right? But that's using the segment addition postulate still.
And notice when they solve the answer here, guys, they just have the 2 points together with no segment symbol above it. You don't remember, we're talking about a measurement here.
Right.
So when we go to label GH, we're going to just call it GH, but with no segment above, because we're actually doing the mathematical approach, not a visual here.
Yep. And so now we want you guys to practice with this.
Yeah.
Okay. And so we're gonna have this number line here, and notice how it's labeled. And so from U to Y is 12 units. From Y to A is 3x minus 3 units. So we said we're going to throw in some algebra on you. And from A to B is 33 units. Okay. Now, what are these other line thingies here, Mr. Vidal?
Well, those hash marks, guys, we're going to use those quite a bit, and those are another way to say congruence on a visual representation of a picture, whatever you want to think of. So when you see that single hash mark there, that means that segment YA is congruent to segment AB. Okay, and so here you just got to kind of think about that. Well, if YA is equal to AB, well, we know that YA is 3x minus 3, and we know that AB is 33, so we can kind of make a quick calculation there to figure
Set up
out
an equation there, yeah.
what X is, and I mean, real simple.
Yeah, we're going to let you do that, though, but we just wanted to tell you what those hash marks mean.
Right.
Okay, and that's how we refer to them. They're called hash marks.
Right. So you're gonna have to try to figure this out, and come into class with what you came up with here, and tomorrow, and we'll go over that.
So these are your 4 questions, and we want you to have the answers to these 4 questions based on this diagram tomorrow. But we'll go through it in class. If you get stuck, we'll go through it in class still. But we want you to have the answers to these when you come in. So pause it here. Maybe draw that diagram in your notes and write down those 4 questions and come up with your answers to those, because we got a couple more slides we want you to do the same thing on. So pause it here and get those. And then same thing here. But now we're moving this to a 2-dimensional coordinate system.
that's right.
A rectangular plane here. And so we're really talking about 2 kind of those number lines, one horizontal and one vertical, but it's the same thing. You can move the ruler and do different angles and so on. And so we want you to answer this question to determine whether JK and LM are congruent to each other or not. And so if they're congruent, they have to have the same length. So see if you can figure out if those 2 segments have the same length or not.
So pause it again and spend some time, look at that, and try to come up with an answer.
With an answer to example 4 is how you'll label that.
Yep.
Okay. And last one here, pretty much the same thing as the first one we asked you to do, except they just give you information. So instead of putting like little hash marks on the diagram, they're just telling you that RS equals ST. And so we would like you to put hash marks on those to represent that. Okay. RT, from R to T, and T to U, those are also equal. Now that's a little bit harder to notate in the diagram. You might want to do like a bracket underneath one of them, bracket underneath the other to show that those are congruent to each other. And then the whole thing equals 68. And we want you to go through and answer these questions. Okay. Sorry guys. Right here, we want you to answer 3 questions. Sorry, I thought there was 4. 3 questions on that number line. Okay, so stop it here or pause it here and write down those questions. So we want you to have the answers to those 3 slides when we start class tomorrow, and we're going to discuss those. All right?
All right.
Okay, we'll see you guys in class.